Hi, I'm Ben-Yaakov. This presentation is entitled Common Mode Chokes, There is More Than Meets the Eye. Now here is the problem that I'm addressing in this presentation. Suppose we have an inverter or converter or some other switch mode unit which is connected to a power supply, and I'm showing here a battery. Now if I'll connect the unit directly to the battery, the current ripple that will penetrate into the power supply coming from the switching unit, will surely be much higher than is allowed by EMI standard, depending on the application. So we do need a filter which is referred to as a common mode filter that will attenuate the ripple coming from the inverter or the other unit into the power supply. Now to measure whether we pass the test, we use the LTspice, which is a line impedance stabilization network, which in essence has the following components. There is a 50 ohm resistor, and then there is a decoupling capacitor on both sides. Here we are connected to ground. And then there are series inductors, 50 microhenry in one standard. There are some other standards for very high frequency in which the inductance is lower. Let's talk about the 50 microhenry. And the purpose of this inductor is to block the current that will be passing here and sort of enforce a circulation of the current in this loop here. Okay, so we can measure the current, the ripple current, by this resistor, by the voltage drop on this resistor. Now the purpose of this common mode filter is to attenuate this injection such that we'll have an attenuation between what is happening here and eventually what we measure here. And supposedly what it means that without the LTspice, this is the current that will be injected into the source, and it has to abide a certain limit. Now we distinguish between two types of conducted EMI, a differential mode and a common mode. Let's talk about the differential mode, which is simpler to understand. And then we have here a ripple on the capacitor. Now if we connect this unit directly to the LTspice, then obviously all this ripple will be imposed on this line here, and therefore the voltage that we'll measure will be just about the ripple of the bus, because 50 ohm is a fairly large resistor for a typical bus. So in this case we'll have a very high ripple, certainly much above the allowed limit by the standard. For this reason we do need a common mode filter, such as to attenuate the signal from the source into here. So the differential mode is the current which is passing this way. Okay, this is differential because it's between the lines. Now the other type of a conducting EMI signal is the common mode, which is a bit different. It's more complicated, both the way it's generated and to explain in fact. And what it is that we do have some capacitances between the switching nodes and ground. This is parasitic capacitances, not something that we are putting in. And due to this fact, we have now another current circulating this way. And in this case, it splits sort of two ways, and it goes into the unit or out of the unit, as a matter of fact, through both the wires. And this is why it is called common mode. So for this, we also need a filter in order to block this current. So in the test, what we are doing is actually to connect a spectrum analyzer to this point, and then we look at the spectrum of the signal that we see here. Now the limits of the standard are usually given as lines here at the frequency domain, the spectrum, and there are different lines for the average and peak and quasi-peak line. It's not that important in this case, and the level is actually changing. It's higher here and then it's going down. Let's say that on an average we are talking about something in the area of 60 dB microvolt, and I'll say something about this unit later on. And actually the standard that I'm referring to is starting at 150 kilohertz, and it goes to the hundreds of megahertz. So this is what we have to watch that the spectrum here measured on these 50 ohms, that none of these lines will penetrate this limit. So this is actually the conducted EMI test. Now what is this dB microvolt? 0 dB microvolt is 1 microvolt. Now 60 dB microvolt that I was referring to is 10 to the third, 60 dB is 10 to the third, times 10 to the minus 6 is 1 microvolt, so it's 1 millivolt. So we are talking about a limit of 1 millivolt such that all the components need to be below that level. So the problem the designer has is the following. We are starting with a ripple here on the bus, and I'm talking about the differential mode, which has a certain level. Let's assume it's something like 0.1 volt for any one of the harmonics of this signal, okay? So this is what is found here. So we need now a common mode filter such that when measuring it on these resistor, 50 ohm, we'll not see more than 1 millivolt about, and more precisely, the limit should be below the level given by the standard. Now for the differential mode, you would have thought that the way to go is to put a filter like that will attenuate, in fact, the voltage here, and such that the voltage that will be detected here will be much lower. However, we are talking about systems that might have a very high current, input current. So if you build a filter that in fact has to deal with ripple, small signal, but you are passing the DC current through it, then the unit will be very large, because it's not only the ripple that will affect the size, but also the DC current. You have to make sure that the core will not go into saturation. So you need a wire that will, of course, carry the current that you have. The diameter should be sufficient. And then you need a core that will not go into saturation. So this is not a practical solution unless you are forced to do it, and I'll talk about it later on. For the common mode, you would have thought that you'll have here like 2 inductors to block this common mode current. Again, the same point here, that if these are separate inductors and a DC is passing through them, they're going to be very large. So this is why we prefer to use the coupled inductor solution, which is the common mode choke. This is called the common mode choke. What it is there are 2 windings on one core, and they are connected to the line and to the unit under test this way that the dots are here. So the current is coming in, going into the unit, and then coming back out of the dot. Here it's into the dot, out of the dot. So the net MMF force, here say it's positive and here it's negative. So the core, ideally, if everything is balanced, does not see any of the DC current. It sees only the common mode. For the common mode, it's like a inductor. This, you can measure it by, say, either on one of them or the 2 connected in parallel. It's the same thing. It's like 2 windings which are connected in parallel. You can think about like one heavy wire that you split it into 2. So it's the same thing. So therefore, we have here a very nice solution to the common mode, and that we can get rid of the power-related current. Now what about the differential? We can use this unit also partially for blocking the differential mode injection, and this is by making sure that we'll have sufficient or a large, relatively large leakage inductance. So if these 2 are not very well coupled, then we are going to have a leakage inductance, and this is in fact a differential mode filter helping to attenuate the differential signal. Now in some cases this is not enough, so you have to add the extra differential mode filter, and then of course there is a problem because of the large current that's now passing, so the core has to sustain this magnetization which will of course require a fairly large core. Now you would have thought that you can simulate this whole issue here by, say, LTspice using coupled inductor, and if you like to add the leakage, then of course you can make the coupling coefficient smaller than 1, and the difference between the value and 1 is of course related to the leakage inductance. Well, not so. In fact, this presentation shows, and this is the purpose of this presentation, that things are much more complicated. It's not just a simple case of two coupled inductor. It's far more involved. So let's have a look first at a commercial common mode choke, and here it is. This is the Worth product. There are many other companies who are making similar, of course, common mode chokes. And you see the construction here. You see that the two windings are put aside as much as possible, and this is in order to, of course, increase the leakage inductance, actually to make a gap here with ferrite material, and by this you actually increase the leakage inductance. I'm not going into the actual construction of the unit. So for this particular unit, it's just an example, the current carrying capability is 1.3 amp. The common mode inductance is 5 millihenries. Notice that it is measured at 10 kilohertz with a 0.1 milliamp signal. Very low, because eventually, if everything works fine, the current that will be passing is small. Anyhow, it's a small signal test. It's not a large signal test. And the resistance is quoted as 200 milliohm. The DC resistance, this has to do with the, of course, heating up of the unit due to the actual current going back and forth. Now, there is no information here about the differential inductance or the leakage, which is important, and it's kind of a pity. And there is a good reason why they are not showing it, because it's complicated, and we'll see it in a minute. So here it is. Let's have a look. This is part of this data sheet, and here they're showing two things: the attenuation and the impedance. Let's first of all look at the impedance. So this is the impedance of the unit as a function of frequency. This is in megahertz unit, so this is 1 megahertz here, and this is impedance in ohm. Now, impedance for an inductor is omega L, 2 pi f L. So you would have expected that this should go up and up and up in a straight line, okay? Because omega is going up, f is going up, and this should go up. Well, not so. You see that it sort of, first of all, tapers off, and then, in fact, it goes down. So the impedance at, say, 10 megahertz is not that high, meaning that the effective inductance is apparently small, because if it would have been the same as here, then we should have seen it, the impedance here and not here, okay? Now, as far as the differential part, which is this leakage, in fact, you see that it starts very low. Well, it makes sense, because this is the leakage is a small inductance, and then it starts to go up, which it makes sense. This is like about 20 dB per decade. And then, however, you have some oscillations here, and then also it goes down. Now, the oscillations are apparently due to parasitic resonance, due to parasitic capacitance of the unit. So you have here resonances, and the reason for this tapering off, I'll talk about it later on. Now, if they're talking about attenuation, that is, how much is this unit attenuate? And this test is done according to CISPR 27, if I remember right. And what it is, that actually it's a attenuation on 50 ohm. Actually, there's 50 ohm at the input, 50 ohm at the output. So this is attenuation, assuming a 50 ohm load. So again, what we see here is, due to the fact that the inductance is not going up linearly, we see that the attenuation is going up to something like 43 dB, and then it goes down, so that at high frequency, above, I don't know, 10 megahertz, in fact, it's only 10-15 dB, that's all, that's what you have. In the differential mode, it's much more complicated because it's not only going up and down as we see here, but it's actually oscillating, or seems to be oscillating. And this is due to parasitic resonance, which is due to the fact that the unit has capacitance, and with this stray inductance, there is a resonance here, and therefore you can see it here as attenuation going up and down, which is sort of a reflection of what we see here. Now, Wood has a LTspice model of common mode chokes, and this is why I've chosen, because I have put here the model of this particular unit, okay? And now I've set up 3 circuits here for different things. This one is for measuring actually the differential mode inductance, because if I short it, then I see here just the differential mode inductance. I'm showing here a voltage source where I did it both voltage and current sources. Doesn't matter, of course, the ratio between them is the impedance. And here I'm measuring the common mode inductance by shorting here and shorting here, so it's just an inductor. And again, with an excitation in AC analysis. And here I'm looking at the attenuation. So I have 50 ohm here, 50 ohm is a load, and I have to look at the voltage here. Actually, attenuation is the ratio between what you get without the filter divided by what you get with the filter. But without the filter, it's of course 1/2, because 50 ohm and 50 ohm, half of the voltage, half of the input, so it's only 3 dB. So I'm going to neglect it in the plots that you will see, because it's just a small fraction of the attenuation. And here, same thing, I have the 2 loads here, and it is connected as a common mode inductor. And here is what I'm getting. So we see that for the common mode, there's a very good agreement. You see it's going up, you see the break, and it's about 43, and here it's also about 23. That's pretty good. Although it doesn't show oscillation at the end, okay? It doesn't show oscillation at the end. On the other hand, for the differential mode, I don't know why, maybe I did something wrong. The fitting is not very good. I see here a much larger attenuation in this peak. I don't understand. Maybe there is a problem with the model. In any event, the general picture is very similar, but the value is not very good. And this is for the attenuation. Now, we can do the same thing for the impedance. And again, a pretty good agreement. Here's the impedance. And you see that it starts here and going up linearly as in the log-log scale, as you'd expect if it would have been just an inductor, and then it tapers off and going down. And the same thing goes for the differential mode. You see that the agreement here is pretty good as far as the impedances go, although the oscillation here are not the same, and also we don't see the oscillation here in the common mode. Again, I cannot explain it, and I don't understand why the difference. Maybe the model is really not very accurate, or I did something wrong, but the point is that we see a very good resemblance between the behavior here and the information given in the datasheet. With LTspice, I can also break down the impedance into the inductance and resistance. And this is by using the operator imaginary, IM, and the operator RE, real. Okay? By using these 2 operators, I can break down the common mode impedance into an inductance and resistance. And what we see is kind of interesting. We see that the inductance is pretty constant, and it is 5 millihenry as specified. The resistance starts with 84 milliohm, and then it goes up, and then both of them are tapering off. For the differential, we see 7.7 microhenry, pretty small value as a matter of fact, and surprisingly fairly high resistive portion. Now, I've tested it also in DC, I've also tested it in large signal, and this number seems to be correct for the model, but it's not correct in reality. This is just too large and doesn't make sense, okay? So this is just a result of the way the fitting was done. Now, as I understand, the LTspice model of this particular unit is done by fitting to some behavioral network, and that's what it came up with, the best it could do to match the attenuation or the impedances, and as a result it came out that there is a resistance of 338 milliohm, which is not real. So why is this behavior of this resistance going up? Well, it turns out that there is an explanation. Now, if we look at the typical permeability of a ferrite, and I'm just showing the 3F3, I don't know what words it's using. 3F3 is not the right core for common mode chokes. Okay, I'm just giving it as an example. All ferrite have just about similar behavior, although not all manufacturers are giving this curve here, this dotted curve, which is important. So this is why I've chosen Ferrox Cube 3F3, because they are showing both the, in fact, real and imaginary permeability. Okay, so what we see is the following. We see that the real permeability is about constant to 1 or 2 or 3 megahertz, and then it tapers off. So the permeability of the unit is going down. Now, inductance is some coefficient times permeability. Well, the coefficient has the number of turns, cross-section, etc., and times the permeability. So if the permeability is going down, the inductance is going down, no question about that. So this is what we see here. The inductance is going down because at around 1 megahertz or a little bit higher than that, it goes down. I don't know what is this dip here. Maybe it's a glitch of the model or whatever. Maybe there is some resonance in it. It doesn't have to be, but this is what we see here. So this can be explained, that the permeability is going down, so therefore you are losing inductance, because the inductance of an inductor is proportional to the permeability. So this explains this thing here. But this dotted line is very interesting. What it shows here is in fact losses. Okay, so what it shows here is as you increase the frequency, the losses are going up. Now, the losses are not given as losses, but as imaginary permeability. So what does it mean? Now, the impedance of an inductor is j omega, some k as we have said, times the permeability, and now it turns out that the physics of the ferrite is such that we have in fact two permeabilities, one real and one imaginary. Now the real is the one we are using here normally. Now the permeability, you see when you multiply the j by the j, you have now a real number, and we are talking about the absolute value. So in fact this permeability, this imaginary permeability, reflects real losses. And what we see here is that at low frequency, up to 1 megahertz, it's fairly small. But as the major permeability is going down, this imaginary permeability is in fact increasing to a very large value. And this, I think, is explaining this fact here, that the resistance of this inductor is going up very high. It has to do with the skin effect or proximity effect of the wires or these losses. So evidently, from what I've shown here, which is just an introduction, we see this common mode choke is a very complex unit, and the behavior of it is far from being simple, and also the attenuation that you get is also not straightforward, because as we can see here, at very high frequencies, sometimes you need quite a bit of attenuation. The attenuation is not that hot, and in fact there are some dips here which may reflect on the value measured on the listen. So this is really not simple. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.